Hi guys, so yesterday we just continued on with our solving systems of equations. Um, we were still using Gaussian elimination, which is essentially getting our matrix into row echelon form. We also talked about the formal definitions of row echelon form and reduced row echelon form. Right. Well, reduced row echelon form, right, whenever we get our matrix in that form, right, is solving systems using what's called Gauss-Jordan elimination, right? And it's a little bit more involved going through the actual steps, right? But when you get to the end, it's actually a lot easier. It eliminates the need for backward substitution. All right, so let's go ahead and take a look at an example of one of these using Gauss-Jordan elimination. All right, so first thing first, we still will definitely want to put our equation into an augmented matrix first. All right, so we will have 1, -2, 3, 9, -1, 3, 1, -2, 2, -5, 5, and 17. Okay, and of course this is my row 1, row 2, row 3. All right, now when we're doing Gauss-Jordan elimination, it's really the same thing as when we were doing Gaussian elimination. We can only worry about fixing one column at a time, okay? Sometimes nice things happen for us with these other columns, but we can't expect that, and we definitely can't force that, all right? So don't try to do too much at once. That's usually when you start messing things up, all right? So uh, first, in my first column with Gauss-Jordan elimination, I want this to be a 1. I want this to be a 0. I want this to be a 0. Okay, so of course this is already a 1, so I'm not going to have to change my row 1. So 1, -2, 3, 9. All right, I want this to be a 0. All right, well, that's easy enough. I can just do row 1 plus row 2. So 1 plus -1 gives me that 0 that I want. -2 plus 3 is 1. 3 plus 1 is 4. And 9 plus -2 is 7. I also want this to be a 0. There's a couple of different ways that I could do it. I could multiply row 1 by -2 and add here. I could multiply row 2 by 2 and add here. And that's actually what I'm going to do. I'm going to say 2 times row 2 plus row 3. All right, so now I'll get -2 plus 2, which gives me that 0 that I want. 6 plus -5 is 1. 2 plus 5 is 7. And -4 plus 17 is 13. All right, so I have fixed this row exactly as I wanted. All right, now with my next iteration, I'm going to, or fix this column rather, sorry. I'm going to want to fix this column, okay? And to get it in reduced row echelon form, I'm actually going to want this to be a 0, this to be a 1, and this to be a 0, okay? So in order for this to be a 0, and do be careful that when you're kind of combining your rows, all right, that you don't combine them in such a way that you will change this column, okay? We don't want to do anything to change that. All right, now if I'm going to get this to be a 0, I can go ahead and say row 1 plus 2 times row 2. All right, so when I do that, I will get 1 plus 0, which keeps that the 1 that I want. I will get -2 plus 2, which gives me the 0 that I want. All right, 3 plus 8 is 11, and 9 plus 14 is 23. All right, here I want this to be a 1. It is. So I don't have to change row 2 at all right now. So 0, 1, 4, and 7. All right, and I want this to be a 0. All right, so I'm just going to go ahead and say row 3 minus row 2. All right, and you could have, of course, said row 2 minus row 3. That still would have given me the 0, but I did it just since this was larger to give me a positive value here. So when I do that, 1 minus 1, 0 minus 0 is 0. 1 minus 1 is 0. 7 minus 4 is 3. 13 minus 7 is 6. All right, now eventually I'm going to want this to be a 1, and since these are both multiples of 3, I can go ahead and just take this whole thing and multiply it by 1/3. And that way when I do that, this will become a 1, this will become a 2. So 1 and 2. Okay, so now with my second iteration, I fixed my second column. So now I'm going to do another iteration to fix my third column. All right, so in my third column, I'm going to want this to be a 0, this to be a 0, this to be a 1, which it already is. All right, but again, now we don't want to change either of these two columns here. All right, so I can really only combine rows 1 and 2 with row 3 because that way these two zeros here kind of won't mess up these two columns. All right, so I want this to be a 0. So I'm going to say row 1 minus 11 times row 3. All right, so that way I get 1 minus 0, which is still that 1 that I want. I get 0 minus 0, which is still a 0. All right, here I will get 11 minus 11, which will give me that 0 that I want. And I will get 23 minus 22, which gives me a 1. All right, now I want this to be a 0 as well. So I'm going to kind of combine it with this again. So I'm going to go ahead and say row 2 minus 4 times row 3. So now I'll get 0 minus 0, which is 0. I will get 1 minus 0, which is 1. All right, I will get 4 minus 4, which is 0. And I will get 7 minus 8, which is negative 1. All right, and then of course I want this to be a 1, which it is, so I don't have to change row 3 at all. So this is 0, 0, 1, 2. All right, so this is now in reduced row echelon, right? Basically, any non-zero, first non-zero number is a 1. The ones are further to the left in higher rows, and any column with a leading 1 has zeros everywhere else. All right. Now, what actually makes this really nice is before, when we just had it in regular row echelon, right, we would say, okay, well, this tells me that z equals 2, and then I would go in and plug z equals 2 up here and solve for y, and then I'd plug y and z up here and solve for x. Well, because of all these other zeros, everything's already done for us, right? This tells me that y is equal to negative 1. And this tells me that x is equal to 1. All right, so my ordered triple, my answer here would be 1, negative 1, 2. Done. All right, so it's a little bit more effort. Remember with like Gauss-Jordan, a lot of times, like we never would have messed with this row at all because once we had the 1, anything after it was fine, right? So like when we were in, if we were just doing Gaussian, we would have stopped right here, right? And we just would have done backward substitution from there. Right? We would have said, okay, well, z equals 2, and then y plus 4z equals 7, which we would have solved y to be negative 1, and then we would have plugged y and z in up here and solved for x. Right? Well, kind of once we get it in this nice reduced row echelon form, it basically just gives us our answers. Okay, so that is the nice part of that. All right, so we can go ahead and look at one more example. Um, for those of you, since I'm recording this, that go back and watch this or whatever, you may want to pause the video, try this on your own, and then unpause it once you're done and see if you got it correctly. But again, we simply want to put this in an augmented matrix. All right, so 1, 0, -3, -5, and 3, 1, -2, -4, 2, 2, 1, -2. This is my row 1, row 2, and row 3 to start. All right, remember, each time through, we fix one column. So the first time, I want this to be a 1, I want this to be a 0, I want this to be a 0. All right, so my row 1 is fine, so I don't have to do anything to it. All right, so we will have 1, 0, -3, -5. And I want this to be a 0. All right, so I'm going to, and again, I'm just kind of thinking ahead here. It doesn't really matter how you do it, but I'm going to say R2 minus 3 times row 1. All right, so when I do that, 3 minus 3 gives me the 0 that I want. All right, 1 minus 0 gives me a 1. -2 plus 9 is 7. And -4 plus 15 is 11. And I also want this to be a 0. All right, so we can say R3 minus 2R1. So that way I will have 2 minus 2 gives me the 0 that I want. All right, I will have 2 minus 0, which is a 2. We will have 1 plus 6, which is a 7. And we will have -2 plus 10, which is 8. All right, so with my first iteration, I fixed my first column. All right, now my next time through, I want to fix my second column. Now I want this to be a 0, which it is. I want this to be a 1, which it is. And I want this to be a 0. All right, so I don't have to change my first 2 rows this time through. So I'll have 1, 0, -3, -5. I'll have 0, 1, 7, 11. All right, and here we can say 2 times row 2 minus row 3. So 0 minus 0 is still 0. 2 minus 2 is 0. 14 minus 7 is 7. And 22 minus 8 is 14. Now, of course, eventually we're going to want this to be a 1. And these are both multiples of 7. So I can literally kind of just divide everything by 7. And when I do, this will be a 1, and this will be a 2. All right, so second time through, I fixed my second column, 0, 1, 0, good to go. All right, now my third time through, I'm going to want to fix my third column. I'm going to want this to be a 0, this to be a 0, and this to be a 1, which it is. Now, again, we have to be careful that we don't do anything that would affect these first 2 columns. So basically, I'm going to be combining row 1 and row 2 with row 3 because these two zeros out here are going to help me not change these two columns. All right, so first, if I do row 1 plus 3 row 3, that will give me that 0 there that I want here. So row 1 plus 3 row 3. So I will get 1 plus 0, which is 1. 0 plus 0, which is 0. Negative 3 plus positive 3, which is 0. All right, and negative 5 plus 6, which is 1. I'm going to do similar here. Right, I'm going to go row 2 minus 7 row 3. So 0 minus 0 is 0. All right, 1 minus 0 is 1. 7 minus 7 is 0. And 11 minus 14 is negative 3. And then, of course, this is fine because this is already a 1. So 0, 0, 1, 2. All right, well, now this is in reduced row echelon form. So essentially, my x is 1, my y is negative 3, my z is 2. So 1, negative 3, 2. And we are done. All right. Let's look at another example. All right, now here we only have two equations with three variables. All right, you can't find a single solution. All right, like we have been. There's not going to be one nice order triple where these things intersect. All right, but this is going to be similar to when we first started solving some of these more complex systems where they can have infinite solutions and they're going to have that certain form. All right, but we can still use the same process here until we get to a certain point. So again, I'm going to make this a augmented matrix. So 2, 4, negative 2, 0. All right, and 3, 5, 0, 1. All right, well, I still want to do the same concept, right? I still, my first time through, this, of course, is row 1 and row 2. All right, first time through, I want to fix my first column. All right, so I want this to be a 1 and I want this to be a 0. So first, I can easily enough just say row 2 minus row 1. And when I do that, 3 minus 2 is 1. 5 minus 4 is 1. 0 minus negative 2 is 2. And 1 minus 0 is 1. All right, now I want this to be a 0. So in order to do that, I'm going to have to say 3 times row 1 minus 2 times row 2. All right, now earlier when I first started explaining how to do these, all right, I said oftentimes you want to use, you have to use every row or equation, which obviously we have, but I said you don't want to like do the same combination of the same two rows twice. All right. In fact, I told you to avoid using the same two rows, at all costs. Well, here we kind of have to, right? We're using row 1 and row 2. We're using row 1 and row 2. One, we don't have another choice. But for 2, we're actually doing very different things with these two rows, right? Like here I was trying to get a 1. Here I'm trying to get a 0. So I'm not doing like constant multiples of the same operation. Right? And that's really what gets us into trouble. So even though we don't like to use the same two rows here, we're going to, and it's going to be okay. So when I do that, I'm going to get 6 minus 6 is 0. Right? 12 minus 10 is 2. Negative 6 minus 0 is negative 6. and 0 minus 2 is negative 2. All right, now also we can note that all of these are multiples of 2. So we could kind of clean this up a little bit and just divide everything by 2. So I would get 1, negative 3, negative 1. So 1, negative 3, negative 1. Just makes our computations a little bit easier down the road here. Okay, so I fixed my first column my first time through. My next time through, I'm going to want to fix my second column. I'm going to want this to be a 0. I'm going to want this to be a 1. This already is a 1, so we're good there. All right, to get this to be a 0, I can just subtract, right? So I can say row 1 minus row 2. So 1 minus 0 is 1. 1 minus 1 is 0. 2 minus negative 3 is 5. 1 minus negative 1 is 2. And then, of course, we said we could just keep our row 2 here. So 0, 1, negative 3, negative 1. So now with my second time through, I fixed my second column. So we're good. All right, we can't go any further here because we don't have any more rows to kind of do anything with. All right, so this is where I say, okay, z is equal to a. All right, so now up here, I can say y minus 3z, which is a, is equal to negative 1. So this is negative 3a. I just add 3a to both sides. So y is equal to 3a minus 1. All right, now I can take my y and my z and plug them in up here and solve for x. If I do that, I get x plus 0y, well, 0 times anything is 0, so that just cancels that out, plus 5z, and we know z is equal to a, is equal to 2. So this is just 5a, so I can subtract 5a from both sides. All right, and we're good. I have my x, my y, my z. All right, so again, this is going to be, there's going to be infinite solutions, but they will all be of the form negative 5a plus 2, comma, 3a minus 1, comma, a. All right, basically what this means, again, just to kind of reiterate what we talked about a little bit before, all right, this will have infinite solutions, but not just any random combination of x, y's, and z's or solutions. They all have to fit this form. So you can pick absolutely any number that you want for a. Let's just, for an easy example, pick 1. So if I plug 1 in here, I would get negative 3, 2, 1. So negative 3, 2, 1 would be a solution, right? I could pick 2, right? And then we would get negative 8, 5, 2. So negative 8, 5, 2 would be a solution. And you can do that with absolutely any numbers you want, right? They don't even have to be whole numbers. You could pick 1.3765, right? You could pick 11 over 7. It doesn't really matter what you pick. They just all have to fit this form. All right, let's look at one more of those. Again, if you're going back and watching this video, all right, this would be an excellent point to pause the video, attempt this problem on your own, and then kind of play to check and see how you did. All right, as always, we want to start with an augmented matrix. So 1, 1, 5, negative 3, and negative 1, negative 2, negative 8, 5. It's a little sloppy here. Alright, so of course this is my row 1, this is my row 2. First time through, I want to fix my first column. I want this to be a 1, which it is. I want this to be a 0. Alright, so first thing I can do is my row 1 we said was fine. So 1, 1, 5, negative 3. Now I want this to be a 0. So I can just say row 1 plus row 2. So I will get 0, -1, -3, 2. All right. So first time through, I fixed my first column. Next time through, I want to fix my second column. So I want this to be a 0, and I want this to be a 1. All right. Well, first I can just say row 1 plus row 2. All right. And when I do that, I will get 1, 0, 2, -1. All right, and I want this to be a 1, so I can really just take the opposite of that row. So I will get 0, 1, 3, -2. So second time through, I fixed my second column. We're good. Okay, of course, again, we don't have as many equations as variables, so I'm really done right here. All right, and this is, again, where I have to start. Okay, well, my z has to equal a. So now plugging that up here, I can say, okay, well, y plus 3z, which is a, is equal to -2. Of course, this is just plus 3a, so I can subtract 3a from both sides. All right, do the same thing up here. So I'm going to get x plus 0y, so that gets rid of that, plus 2z, which is a, is equal to -1. So of course this is just plus 2a, so I can subtract 2a from both sides. All right, so the general form of my solution, of my infinite solutions here, will be -2a minus 1, comma, -3a minus 2, comma, a. All right, and of course the same thing applies here. You can pick any number you want for a, plug it into all three of these, and it will give you an x, a y, and a z that would solve your system. All right, that's really it for today. All right, as far as solving systems. All right, so now you can use Gaussian elimination, which is when you put your system in row echelon form, or you can use Gauss-Jordan elimination, which is what we've been doing today, when you put your matrix in reduced row echelon form. All right, now before we completely stop here, I do want to actually show you how your calculator can do these things very efficiently. All right, so we'll just go back and take a look at this first one that we did. All right, and we already put it in the augmented matrix here. So if you go here, second, and then this x to the -1 to take us to that matrix menu, which we've looked at before. All right, we can go ahead and edit my matrix A. All right, this is going to be a 3 by 4 matrix, because we have 3 rows and 4 columns. All right, and then I just go ahead and enter all of this stuff into my matrix. So I'm going to have 1, -2, 3, 9, -1, 3, 1, -2, 2, -5, 5, and 17. All right, so once they're all in there, you can go ahead and quit out to your main screen. All right, now, if you go back to your matrix menu, right, if you actually go over here to math, right, you can go all the way down if you want, but actually if you go up, it's a little bit faster. This RREF stands for reduced row echelon form. All right, you can also come up here, obviously REF is just row echelon form, but why not take it all the way to reduced row echelon form if we're going to let the calculator do it. So you hit enter on that, it pulls it out to your main screen. All right, you go back to your matrix menu, and under the names column here, you hit enter on A, because that's the matrix that we want to put in reduced row echelon form. All right, and when we do that, okay, what do you know? It's the exact same as what we got when we went through and did it by hand. Right? So this tells us that x is 1, y is -1, z is 2. All right? So your calculator can do that very, very efficiently. All right.